Hello everyone. In this lecture, I am going to explain about Gibbs Helmholtz equation. I have selected 4 questions for better explanation about this equation. One from BSc Part 2nd exam 2018. Second one from 2016 exam of BSc Part 2nd. Third is from IIT GATE exam 2019. And last one is from the CSIR 2018 June exam. By the help of these 4 questions, I am going to explain Gibbs Helmholtz equation. Now, I am going to comment on these questions one by one. First question is from BSc Part 2nd exam 2018. The question was that for a closed system, derive Gibbs Helmholtz equation in terms of change in Gibbs free energy and enthalpy change. The second part of this question is discuss its application. Next, the second question is BSc Part 2nd exam 2016. That was derive Gibbs Helmholtz equation, and its B part is a numerical question in which free energy change in a process is minus 87.77 kilojoule at 25 degrees Celsius and minus 83.66 kilojoule at 35 degrees Celsius. Calculate delta H at 35 degrees Celsius. At 2 different temperatures, delta G is given here, and at 35 degrees Celsius, this question demands delta H. Now, in IIT GATE exam 2019 question was that consider the electrochemical cell. One electrochemical cell is given here, concentration cell. Now, where M is a metal at 298 Kelvin, the standard reduction potentials are given here, and the temperature coefficient is given, that is delta E by delta T. At this temperature, the standard enthalpy change for the overall cell reaction, delta H is what? In kilojoule per mole. And these informations are given here. Question is that by given different parameter, I have to calculate the delta H, standard free energy, standard enthalpy change of this reaction by the help of these things. Now, the CSI question 2018, that was question number 118 of code C in July exam. The standard cell potential of cell, one cell is given here, was measured over a range of temperature and the data was fitted as. Here, equation of a standard EMF is given here. Now, the standard reaction entropy, that is in joule per Kelvin per mole, and enthalpy, that is in kilojoule per mole, at 298 Kelvin R, and options are given here. This is the CSIR question. Here, expression of standard potential is given in the terms of in the variable quantity temperature, and now I have to calculate the entropy and enthalpy for reaction in these units. Okay, after that, now I am going to solve question first, that was from BSc exam, and similarly one by one I am going to explain all these questions in this video. Then the question first was that I have to define Gibbs Helmholtz equation in the form of delta H delta G, in the terms of delta H and delta G, that is change in enthalpy, change in free energy. So first of all, I want to say something about Gibbs-Helmholtz equation. Gibbs-Helmholtz equation gives variation of delta G upon temperature at constant pressure. This is the main outcome of this equation. How the change in free energy varies with temperature. There are many forms of Gibbs-Helmholtz equation. The first form is delta G is equal to delta H plus T into delta G by delta T at constant pressure. This is Gibbs-Helmholtz equation. Now, second form is also G is equal to H plus T del G by del Tp. Another developed form of this equation is also that is delta G by T del 1 by T at constant P is equal to delta H, or del G by T del 1 by T at constant P is equal to delta H. So, there are mainly two forms of this equation, and the developed equations mapping from this equation we can achieve this equation, from this equation we can achieve this equation, and both have, this equation has theoretical importance, this equation has experimental importance in chemistry. So we study about this equation one by one. So first of all, I want to prove delta G is equal to delta H plus T delta G by delta Tp. This equation is Gibbs-Helmholtz equation in the form of delta G and delta H. That was our question. So I am going to prove this equation, and what is the importance of this equation, that is explained by the help of numerical question. So the condition on which this equation work is, first, the system must be closed. System must be closed. That is, there is no mass transfer from system. And second is pressure must be constant. that is system pressure is equal to the external pressure. External pressure. Now, let the one system is that the initial condition of the system is given 1 and final state is given 2, and this state and this state are equilibrium state. This is also equilibrium state. That is 1, 2, both are in equilibrium state. Then at first, and the process is isothermal, and the process is isothermal, that is temperature constant. On next page, so I have taken one process in which the first initial state is represented by 1, final state by 2, and both these states are equilibrium state. Equilibrium state. These are equilibrium states. Now, at this state, G is equal to H minus Ts. This is the relation between G and H. G is equal to H minus Ts, where G is free energy, H is enthalpy, and S is entropy, T is temperature. Okay. Then at first state, initial state, G1 is equal to H1 minus Ts1, because temperature is constant here, so T is taken constant. Now at second state, G2 is equal to H2 minus Ts2. This is equation first, this is equation second. By subtracting second and first, we get G2 minus G1 is equal to H2 minus H1 minus T S2 minus S1. S2 minus S1. This is third equation. Now, G2 minus G1, that is called delta G. H2 minus H1, this is enthalpy change. T, and I leave this form as it is. S2 minus S1. Okay. Because entropy cannot be experimentally calculated. So, entropy is converted into another thermodynamical relation form. So, for this, I am going to define G. Now we know G has independent parameters T and P. That is, free energy has independent parameters temperature and pressure. So, differential form of this is dg is equal to minus sdt plus vdp. Now, at constant pressure, vdp becomes 0. So, S sorry. So, minus S can be written as delta G by delta T at constant pressure. Here, temperature is a small variation in temperature is given here, and for the two states, that is 1 and 2, second state, if del T changing temperature is here, del T temperature changing is here, then what is the effect on this equilibrium state that I want to see. So, del G1 by del T P is written as minus S1 and del G2 by del Tp is written as minus S2. Okay. Now, putting these values, in equation 4. So, this is a fourth equation, this is my fifth equation, this becomes sixth equation, and can write this is 7 and this is 8. So, once again, this is first state, this is second state, or called initial state and final state. This is initial equilibrium state, this is final equilibrium state, and by changing delta T, I want to relate delta G and delta H. So, at this state, G1 is equal to H1 minus TS1 from the definition of G, and from definition of G, G2 is equal to H2 minus TS2. Now, by subtracting these equations 2 minus 1, we got this equation, and now from the independent variable of G, these are independent variables, dependent variables. G is equal to, G varies on T and P, so this is equal to minus SDT plus VDP at constant pressure, because our system is at constant pressure, so this term becomes 0, and now mathematically this becomes minus s del g by del t. Now for initial state del g1 del t, by changing del t, infinitesimal small changing in temperature, we got minus s1 and this is minus s2. This is minus s1 and this is minus s2. Again, so we are here, delta G is equal to delta H minus T S2 minus S1, and I have calculated minus S2 is equal to del G1 del G2 by del T constant P, and minus S1 बराबर del G1 del T constant P. So by putting this and this equation 4 becomes del G is equal to del H minus T, and S2, the place of S2, this is minus del G2 by del T P, and this becomes minus plus, this becomes del G1 by del T P. Okay. Now by multiplying with minus 1, this minus 1, this becomes T, and this becomes minus T. There is minus T S2. At the place of S2 I have replaced this and this one, and this is minus form here, so minus plus T del G2 by del T, and this becomes minus del G1 by del T P. Okay. Now delta H plus T, and this is free energy, this is free energy, so same quantity can be subtracted here. So G2 minus G1, mathematically it can be written as this, and G2 minus G1, that is our delta G by delta T, and P, this is delta G. Here I am comment out 2 points. First, this is free energy change. This is enthalpy change. And this term is variation in delta G with respect to temperature. That is, if we take delta G here and T here, then what is the slope of curve? At constant pressure, this quantity is delta G by delta T. Free energy change. Derivative of free energy change with respect to temperature. Here, if at two different temperature, I have delta G1 and delta G2 given, and in question, if I have to calculate delta H at T2 temperature, then this equation, again I want to explain this, at two different temperature, change in free energy is given, and if at T2 temperature I have to calculate delta H, then this equation is useful for calculation of delta H. By giving T is replaced by T2, delta G is equal to delta H plus T2, and here delta G2 minus delta G1 by T2 minus T1. This gives the delta H. This is the numerical question of our BSc Part 2 2016 exam, that is free energy change in process is itna and itna, then calculate delta H at 35 degrees Celsius. So this question can be solved by applying this equation, and in this way I have proved the or relate delta G and delta H in the form of this equation. This is the Gibbs Helmhotz equation. Thank you.